Hi everyone. All right, so we're gonna continue the talks on um, these linear operators by giving an example, and then we'll get into some properties, lemmas, and other things about these places. So let's look at an example. So last time, remember, we started off with some linear operator. So here we're gonna define first a linear operator. So here we have a linear operator, and basically what I say is that I given a basis, I'm gonna let P of E1 be equal to E1, and P of E2 I'm gonna send to E1 plus 2E2. And the question is, what's the matrix of P? So what's the matrix of the linear operator given this basis? And then does P of B actually define a basis or not? So here, if we kind of recall P of B, this is just the matrix where we look at things by columns. So here, we have space, but I'm going to open this up a little bit. Oh, man, not enough space. Okay, so I'll just rewrite this on the side. E1 is equal to E1, and P of E2 is equal to E1 plus, where did my answer go? Oh, there we go. 2E2. Okay. So first we want to ask what's the matrix, right? So what's the matrix? This is just P given our matrix B. And again, this is column vectors. So here, this one is the column vector 1, 0, because we have one E1 and no E2s. And this was the column vector 1, 2, because there's one E1 and two E2s. So this gives us 1, 0, 1, 2. Easy, done. Okay, so what you can now do is look at this matrix, and we ask ourselves, is this invertible? This is not hard to see, right? Remember that it's invertible if the determinant is non-zero. And here we see the determinant is 2, so it's invertible, which is invertible. So therefore, that gives us a new basis. And remember, this basis is given by precisely this. Is a basis. So this was P of E1. This is E1. And P of E2 is E1 plus E2, E2. So this as well gives us an ordered basis. And in this case, P of B is precisely the transition matrix from, so we've kind of talked about this a couple of times. This is precisely the transition matrix going from B to C. Hopefully this helps clear up some of the squabbles that I was randomizing last lecture. So hopefully that makes a little more sense now. All right, so now what we want to do is we want to look at linear operators and vectors in general. And we want to look at them in different bases. And so we're going to introduce some notation to kind of fix things kind of in our brain. So some notation. We're going to have some basis vector B, some basis B, and V is going to be some vector in our vector space. So here we'll have B is a basis and V is a vector. So the column vector of V, well, what is this? So remember that V itself is always going to be some linear combination of some VI, EI in our vector space, right? This is how, that looks like an N. Some linear combination. And here we kind of already saw exactly how we should denote this, right? I kind of snuck this in last time. And it's just looking at the entries one at a time. So here we'll have this notation for the vectors themselves instead of the matrices. So this is, yeah. So it's very similar to the linear operator. So this notion also is linear. So remember what we're talking about with linear is that we can take something inside brackets and we can pull these out and separate them. And that's basically what we do going here, but like in a backwards step. So here, if you kind of see, this is not too hard to see. It's just matrix stuff that I'm sure you've seen a million times before, which is why it's not hidden. But you just take lambda times some vector in the basis. So that'll give you a column. We add these up, we multiply things together, and we get exactly what we want. So that's nice. Furthermore, what we actually have is that these matrices are extra nice because we can just use these matrices to kind of calculate things, right? So if I have some vector P of V, right? So P of V, and I want to know what its matrix is, like what its column vector is, right? So P of V is going to give us some linear combination, right? What is its column vector going to be? Well, this turns out we can just take the matrix of the linear operator and we just multiply by the column vector of V of B. The proof is left as an exercise. The proof is left as an exercise because it's just doing calculations, so it's not beneficial to really see, but it's worth kind of seeing how it kind of works. So I'd recommend testing it out, muddying the waters, having a little fun. Okay, so we have this multiplication, right? But what does this affect on the transition matrix on column vectors in a given basis? And that actually gives us the next lemma. So what's the next lemma saying? So the next lemma is saying if I have two bases, so I have two bases. In some vector space V, and we're gonna denote T by BT of C, and this is gonna be the transition matrix from B to from B to C, right? So again, from basis to basis. What we end up having is the following. If I look at V of B, so here, try and maybe stop the video and try to guess what would happen here. What should be after this equality? A little hint, if you need, look at proposition 1.39, and here we basically just took something and we multiplied things. And here we basically get an identical thing. So here we end up getting just T of V of C. And that's it. So we go from B to C. B to C. So let's look at a proof of this. It's not too bad to see. Here we're going to let T equal to BTC just for ease of notation. The ith column of T is precisely Fi of B, right? So if we recall the matrix for BTC is given by F11, F12, F21, Fn1, F12, F22, etc., right? So the column Fi is precisely this one somewhere in the middle, kind of. So in other words, this is going to just give us T, which is the transition matrix, right? Times the EI. So this is EI. And here we have the ith row. I guess maybe this is not EI. This is, yeah, it could be some other EI. And this is the ith row. So this just gives us this precise kind of definition. And in fact, this ith row, the ith row, I'm saying there's a 1 in the ith row and zeros everywhere else. I guess we should have little zeros here. But this, in the basis of C, is precisely just Fi, right? So this is why this transitions into this. So we have this on just one vector, but we need to generalize this to so we have this for the basis vector, but we need to generalize to any vector. So here, what we basically have to do is we take some vector, so TV of C, right? So we've now started on the right-hand side. We're going to decompose this V into its linear combination, which is okay because this is a basis, right? So this does exist. Then by linearity, or not even by by linearity, by distribution, we put the T's on each side. So here, maybe this might help a little. V1 F1 C plus T of Vn Fnc. Then we basically use this previous result here. We use this previous result to get there. So this equality then transforms each of these into that. And then we put this together and we get v of vb. Precisely that. How much longer? Okay, it's not too bad. So we'll just finish the section before ending this video. Okay, so the next kind of two properties we're going to do hand in hand. So this is, sorry for all the lemmas and things, but it's nice to kind of see how these things interact with other vectors, with matrices, etc. So we're kind of putting everything together at this point. So if we take 3 bases now, and I want to go from B to D, but I want to kind of go in between C. So I kind of want to do something like this. I want to go from B, I want to go to C, and then I want to go to D, right? Oops, that was not a D. But we know what this is. Or no, we don't know what this is. We want to ask, what is this? I want to go from B to D, but I know what B to C is and C to D is. How do I kind of calculate this? And this is exactly what you would think. So we would first go from B to C, and then we would go from C to D. And yeah, so all this is just a combination, multiple combinations of this lemma 1.4, right? So we have this through the vector. And so we can just play this game one at a time to get the Ds. And then applying this to the entire transition matrices, we get exactly what we want. So it's not too hard to see this. It's fairly fun. But it kind of makes it nice that going from B to C to D gives us precisely the same thing as going from B to D. Another thing, and this one we're going to leave as an exercise for y'all to do in the homework this week. Oh, I put homework. This should say exercise sheet. It's not in the homework. Then what we have is the transition matrix from B to C, or I guess in this case C to B. This is just the same thing as the inverse of the transition from B to C. So in other words, if I go from B to C, this one we said is B, T, C. The reverse, which is normally denoted C, T, B, this is just the inverse of the first one. And one last proposition before we kind of end things. So basically these lemmas are really just giving us a way to translate between column vectors from one basis to column vectors on another basis. It's allowing us to do all these things, also coming from linear operators. So we're kind of putting everything together into one nice conglomerate of things. And so like bringing this back to linear operators, what we end up having is the following proposition. Now, if P is a linear operator acting on a vector space V, and we let B be some basis, C be another basis, so we have 2 bases, and P a linear operator, and we let T be the transition matrix from B to C. So T is a transition matrix from B to C. Then what we end up having is the following. We end up having that the linear operator matrix, the matrix of the linear transformation P of C is equal to the inverse of T times the matrix of the linear transformation P on the basis B times the matrix T again. To kind of see this, it's just a small little proof. It's not too bad to see. And basically what we end up having is we start off with some, so we start off with some vector here, Fi. And then here we convert this into going to B. So here we want the inverse of T, right? So this is coming from lemma 1.4. So where's lemma 1.4? So here we have T, but we have C on the left and B on the right, right? For ours. So what we have here really is this is CTB, which is going to be the inverse of T, which is BTC, right? That's where this inverse denomination is coming from lemma 1.4. Then we can split this up. And where's this split coming from? This we saw as well. This is also, this is coming from proposition 1.39. I guess we'll put this here. So this proposition 1.39. And then finally, this matrix here on the right-hand side, this we can split up again, right? So this is again from lemma 1.4. 1.4, we get T of F1C, right? So these two are the same. And then here we have precisely kind of what we want, right? So we have that P of C is just precisely our transition. So the ith column of this, yeah, this is just the ith column, right? So this is just one column vector. So now playing this out with every column vector gives us precisely this equality on the matrices. So this is just, so a key part here is that this is just the ith column. So doing this for all columns gives result. So a quick remark before we end the talk for the video for today, or for this lecture. What this proposition is basically showing is that the matrix of the linear operator isn't determined by the linear operator alone. That, in other words, we have to have some choice of basis must be made. So even though like the linear operator itself doesn't depend on a matrix, on the basis, if we want to find the matrix, we need some choice of basis to be able to do this. So we'll end this video here for now. In the next video, we're going to talk about determinants and traces of linear operators and kind of see what makes them cool, what makes them tick, and what makes them exciting. So I will see you in that video. Peace.